So today in 5.1, we're going to be estimating areas using finite sums. So basically, we're going to be looking at the area underneath a curve, as you can kind of see from down here. Now, the way that we're going to calculate area is using rectangles, because rectangles are just the easiest, one of the easier objects to find the area of. All we have is length times width. So if we're going to look at finding the area under the curve y equals x squared from 0 to 1, we know that this is basically, you know, that y equals x squared is a parabola, that the distance between 0 and 1 is 1. So if we're starting at 0 and going to 1, this is the true area underneath that, the shaded part right there. Now, because we're going to be using finite areas, we're never going to get the true, or finite sums, we're never going to get the true area down here. We're just going to get a good approximation, or a decent approximation. If we break this interval from 0 to 1 into two approximating rectangles, this is going to be a delta x, a width. So if we take this total distance, 1 minus 0, that's a distance of 1, and divide it by 2, that tells us that the width of each of our rectangles is going to be 1/2. So this right here is 1/2. This right here is 1/2. This is using the left endpoints for the height of the rectangle. This is also known as a lower sum right here. Now, the area of that we're calculating, the approximation of the area under here, is going to be the area of this first rectangle, which is a height of 0, or f of 0, that is 0 squared, times the width 0.5. That's this right here. The rectangle that we're seeing right here is going to have a height of f of 0.5. So we have f of 0.5. We would plug that into our function right here, and then we're going to multiply that by the width. That's how we're going to get the area of that. And now that's clearly an underestimate because we're missing this piece and this piece of area. If we're using a right endpoint or an overestimate here, instead of using the left endpoint as the height of our first approximating rectangle, we use the right endpoint as the height of our first approximating rectangle. And you'll notice that here, the width stays the same. This is still a half. So that's what this is. That's the width right here. The height right here is going to be f of this first piece there. So f of 1/2. So that's what we're getting right here. So f of 1/2 times 1/2, that's going to be the height here. That's this. This right here, this rectangle, all of a sudden, the y value is going to be associated with the x value of 1, this right endpoint here. So to find the height of this, we're finding f of 1, and we're plugging 1 the function value right here to get that height. The width is still 1/2. We add these together, that's going to give us this, but this is an overestimate. Really, we could take the heights at any point in here to get some good estimates, but classically we do a left endpoint, right endpoint. So a left endpoint would be an underestimate for some things, an overestimate for others, depending on its increasing or decreasing function. Right endpoint similarly. Midpoint is going to give us a better approximation for this right here. Now a midpoint, if this rectangle starts at 0 and goes to 1/2, the midpoint of that would be halfway through, so 0.25, that's going to be our height. That's why we have this f of 0.25. That's going to give us the height of this rectangle. The width is 1/2, that's that. Now, if we're talking about halfway between half and 1, that's 0.75, so the height of that's 0.75. So f of 0.75 is giving us the height of this rectangle, and that's going to give us the width. Now, a couple things to think over this. The more rectangles we have, the better estimate we're going to get. If we have 4 rectangles up here rather than 2, we're going to get a better estimate. If we have 8 rectangles, we're going to get even better, 16, and it doesn't need to be a multiple of 2. You could have 100 rectangles. You're just going to get better and better approximations with the more and more rectangles you have. Now, we want to pick equal length intervals. It's going to be easier to calculate these things. We call these delta x's, so that's a little change in x. So here we pick 2 rectangles. If we go back to here, this is A, this is B. It's always B minus A over N to find out what an equal width would be. Here our N is 2 because we have 2 rectangles, hence 1 minus 0 divided by 2 is 1/2. That's why we're getting these 1/2s. Is that. Now, the next thing is given a velocity function, we can find the approximate displacement with finite sums in a similar way. Now, we want to talk about displacement for 1 second versus distance traveled. If we throw a rock up, its height at any point in time is going to be the displacement, the distance from the place it was thrown to the height it is. Now, that's displacement. The total distance traveled, well, when it goes up, it has a specific amount of distance. When it's going down, it has a specific amount of distance. So the rock has really traveled whatever this distance is times this distance at that time point, where the displacement is just the distance right here. So the total distance traveled, we can approximate this using the same notion of rectangles, where we take the velocity at a specific time, the absolute value of that, so really the speed, times some delta t, some sort of change in time. And this is really giving us a height of this function, and it's giving us a width of the function. So we are really finding the area of a little rectangle here. Plus, if we just move over to the next little rectangle, find the area of that, plus the next rectangle, the next, and the next, next. Now this you'll notice has n rectangles, so it's arbitrary, but once we get a real value for n, we can calculate this fairly easily. Now the average value of a non-negative function, a non-negative continuous function, is going to be this. Now it's don't sweat this one too much. All we're saying is if this is a continuous function, which means I can pick this up without taking my pencil off the paper or cursor or whatever off the paper, and it's non-negative, so you notice this is above the x-axis the whole time. The amount of area down here we can find is the amount of area down here. And we can make this into a rectangle. Now, if we take the total area underneath this curve and divide it by this total distance, well, the distance from A to B is going to be B minus A. So if we take this total area divided by B minus A, that's going to give us what the C is. But if we have any non-negative continuous function, we can always find this value of C, and this is the average value of that function right here. Now, excuse me. If we're using finite approximations to estimate the area underneath the graphs of some functions, using A2 lower sums, B2 4 lower sums, C2 upper sums, D2 upper sum rectangles, and we're using rectangles for all this. I'm just going to run through this example really quickly. If we have a function f of x equals 1 over x, and we're trying to find the area underneath this curve, which basically looks like this between 1 and 5, well, we can use this using lower sums really quickly. Now notice, if we're using two rectangles and we have the distance between 1 and 5, this total distance, 5 minus 1, is 4, okay? If we have the total distance here of 4, and we're going to use two rectangles, 4 minus 2 is 2. So in A, the width of each of these rectangles is 2. That's what we're getting here. That's our delta x. That's our delta x right here. The next thing you can notice is this, is up here, this is the lower sum, and we're using the left endpoints because this is an increasing function. But down here, because we have a decreasing function, the right endpoint is going to be the underneath part, the lower sum here. So here, if we're going to find the area of this rectangle right here, the width is 2, the height is whatever the function value is at 3, that's what this is right here. This piece right here, if we're going to find the lower sum of this rectangle, well, the lower part is going to be at x equals 5. So the height there is going to be f of 5 times the width 2. Well, when we apply f of 5, we're plugging in this function, 1/5 times 2, f of 3, 1/3 times 2. 2/5 plus 2/3 is 16/5. So that's going to be this. Now B, we're going to use 4 rectangles. So rather than having this delta x be 2, the total distance traveled between 5 and 1 is 4. So if we take that and divide it by our 4 rectangles, well, 4 divided by 4 is 1. So notice down here that we have a 1 here, that's our delta x. That's a 1 here, that's our delta x. The 1 there is delta x. Because we're starting at 1 and going to 5, we just go 1, 2, 3, 4, 5, as opposed to when we're counting off by 2's right here. So we're still doing a lower sum. And because this is decreasing, we're going to want to use the right endpoints. So for this first rectangle, 2 is going to give us the lower endpoint. So f of 2, that's going to give us the height. 1 is the width. That's what the 1 comes from. This next rectangle right here, the second one, f of 3, that's what this comes from. Width is 1 right there. Next one over, f of 4, that's the height. Width 1, so we have here. And then f of 5, height is 5, width is 1. Plugging these back into this function right here. So when we do that, f of 2 is 1/2 times 1, so just 1/2. F of 3, 1/3. F of 4, 1/4. F of 5, 1/5. Add these all up, 77/60. Okay. Now, C and D, we're basically doing the same thing, but we have an upper sum using 2 rectangles. So 2 rectangles, distance between 1 and 5. 5 minus 1 is 4 divided by 2. Our delta x is going to be 2 for C. And for D, our distance is 4 divided by 4. Our delta x is going to be 1. So kind of A and C kind of mirror each other a little bit, and B and D mirror each other a little bit. The only difference is because we're doing upper sums right here, rather than using the right endpoint to go underneath the curve, in C, we're going to use the left endpoint to go over the curve. So when we calculate the height of this rectangle, it's going to be f of 1 times our width 2. This one, f of 3 times 1. Well, 1 divided by 1 is 1, times our 2 is 2. 1 divided by 3 is 1/3, times 2 is 2/3. 2 plus 2/3 is 5/3. Here, we have 4 approximating rectangles between 1 and 5. And we're doing an upper sum. So the upper sum right here is going to be, well, left endpoint again, because it's going to give us the higher of the two. The left endpoint gives us the higher, the right endpoint gives us the lower. So f of 1, that's this right here, times the width 1. F of 2 times 1 the width. F of 3 times 1 that's width. And f of 4. That should be a 4, not a 1 right there. What's going on? Applying the function 1 over 1, 1 over 2, 1 over 3, 1 over 4 times the width of 1, adds these up 25/12. Now, you could do a midpoint for this. If you're going with 2 approximating rectangles using a midpoint, once again, the distance between 1 and 5 is 4. If we divide that by 2, we get 2. So the widths don't change. This width is still 2, this width is still 2. If we had 4 approximating rectangles, you know, total distance of 4 divided by 4 would give us a delta x, or a width of 1. It just changes where we're taking the function value. Using midpoints here, well, the midpoint between 1 and 3 is 2, hence f of 2. Plug it into the function, 1 over 2 times our width of 2. Midway point between 3 and 5 is 4. So we have 1/4 times 2. Add them up, we get this. So I hope that has made some sense, and we'll see you in the next video. Okay, so now what we're going to do is we're going to find a little bit, we're going to estimate velocity, or we're going to estimate total distance traveled using velocity. Now, a lot of the time, what they're going to give us is they're going to give us these tables, which is just as good as a graph, because we could plot these out. This is basically saying that at time 0, the velocity is 0. So we could have the ordered pair 0, 0. Same thing, time 10, excuse me, velocity 44. So we could have 10, 44. 20, 15, 30, 35, 40, 30, 50, 44. So what we're doing is we're using 10-second intervals to estimate the distance traveled. Now, first we're going to use a left endpoint method. So basically we're going to use the velocity at the left endpoint of a rectangle. Then we're going to use the velocity at a right end of a rectangle, and we're going to calculate the total distance traveled, because remember, distance equals rate times time. So velocity is a rate times this time. That's giving us a distance there. So when we do this right here, if you think about this as being a rectangle of width 10, the left endpoint of that rectangle, if you can kind of think of it graphically as these values on your horizontal axis and these values kind of being in a vertical axis, the rectangle that starts at 0 and goes to 10, the left endpoint would be 0, the right endpoint would be 40. So we want to think about that. Now, the rectangle that starts at 10 and goes to 20 in width, so that's going to be on the horizontal axis. The left endpoint is going to be 40. The right endpoint is going to be 15. Now, recall from before that we have height times width, or length times width, where length is the height here. The widths here are the same. We're using 10-second intervals. So the distance between here and here, here and here, here and here, here and here is 10. So if you look down at this left endpoint, 10 is the width, 10 is the width, 10 is the width, 10 is the width, 10 is the width. Now the left endpoint, well, this first approximating rectangle, because we're using a left endpoint, is going to have a height of 0. That's where the 0 comes from. The second little approximating rectangle goes from 10 to 20. That gives us our 10 here. The left endpoint of this is going to be 44. Going here to here, 20 to 30, still a 10-second differential, a delta t, if you will, of 10. That's giving us 10 right here. Now the left endpoint is going to be 15. Here, the difference between 30 and 40 is 10. Left endpoint gives me 35. And then finally, the rectangle that goes from 40 to 50 with 10 again, left endpoint's 30, that's what we get. Now, if we calculate this all out, 0 times 10, 0, plus 44 times 10, plus putting calculator, we're going to get this to be 1,240 feet, because this is time in seconds, feet over seconds in velocity. So feet per second, seconds times seconds canceled. This gives us something in feet. Now, that gives us the left endpoint. If we want to do the right endpoint, it's almost no different. Like this rectangle's width, and this rectangle's width, and this rectangle's width, and this rectangle's width all stays the same. Those are all 10, 10, 10, 10. And rather than using the left endpoint, we're going to use the right endpoint. So the width here is 10. Rather than starting at 0, we start at 44. So basically, we're not starting at 0, we're starting here at 44. Next one will be 15. Next one will be 35. The next one will be 30. So we have all those. But this final rectangle, because we're using a right endpoint, will be 44. So in addition to this distance traveled, which you'll notice is really just A, it's going to be, we have to add on this last little piece of distance traveled, which is a time elapse of 10 seconds. So our delta t is 10 seconds. The speed there is the right endpoint, so we're going with the right one of this, not the left one, if we think of these on the horizontal axis. So we have 10 times our 44. We take A times 10 times 44, so 440 plus this is going to give us 1680. That's going to be 1680 feet. Now, the last one I'm going to just skim through really quickly, and you'll notice that the videos that I'm going to try to cut are going to be like this, me running through the examples that are already done, and then in class we'll be doing the examples that we haven't done, or the companion examples on there, and then having you guys do some. So if you want to use finite sums to estimate the average value of a function of f on an interval using 4 subintervals of equal length using midpoints, first thing we have to do is calculate the area. Now, if we're going to find the average value, that's the average like y value, what's the average height of this function? If we're looking at this f of x equals x cubed, that at least from 0 to 2, it's going to look parabolic. You know, if we're using 4 subintervals, well, the distance between 0 and 2 is 2. 2 minus 0 is 2, divided by 4 is 1/2, so our delta x is that. If we're using midpoints here, you know, we're going to be going from 0 to 1. 1/2 is our width, then 1/2 to 1, then 1 to 1, 1/2, and then 1.5 to 2. But because we're using the midpoints, we want to go halfway between 0 and 1/2, which is 1/4, which is what we have right here. We want to go halfway between 1/2 and 1, which is 0.75. That's what we're applying the function to find the height right there. Halfway between 1 and 1/2, that's 1.25. That's what we see right here. And then finally, halfway between 1/2 and 2 is 1.75. That's what we have right here. Now, these widths stay the same. That's a half, that's a half, that's a half, that's a half. So our estimated area here is f of 0.25, which is 1/4 cubed, because we're applying this function value to find our height times our width. F of 0.75, that's finding the height right here times the width. F of 1.25, that's our height right here times width. F of 1 3/4, that's the height right here, times the width. If we multiply all this out in our calculator, we get 3.875. This is the amount of area that we're estimating is under the curve using the midpoints. It's not the true amount of area, but it's what we're approximating the area to be. If we want to know what the average height or average y value is on that, we just take our area, divide that by the total distance traveled in x. Well, here, if this is our a and this is our b minus a is going to be 2 minus 0. We have our area, 2 minus 0, divide that out. So 1.9375, that is saying that is the average height of this curved function between 0 and 2. We know because this is an estimate area, this is an estimate of the average value, but as we use more and more rectangles, we get a better and better approximation of what the true average value of this is. And as we use more and more rectangles, we get a better approximation of what the true value is of this. Now, I know that we don't want to talk about limits because those are bad, but think about this for 1 second. If we take the limit of n being the number of rectangles as it goes to infinity, if we have an infinite number of rectangles underneath this, and we're calculating the area of an infinite number of rectangles rather than a finite, we're not going to get an approximation of the area under this curve. We're going to get the true area under the curve. Similarly, if we think of the widths of these as delta x's, which they are, if you think about the width of them going to 0, the width going to 0 would mean that you're having these really, really skinny rectangles, and you're going to have an infinite number of rectangles again, so we're not getting the average value, or the average area underneath, or some approximation of the area underneath the curve. We're getting the true area under the curve, so of things to come. So that's going to be it. We'll see how long that video was, and then I'll post this to Canvas soon.